So we continue our solution to exercise 118 with two more parts today. Let us just see once more what it was all about, because it's been some time. So we have a ring homomorphism F from the ring A to the ring B. I1 and I2 are two ideals of A and J1 and J2 are two ideals of B. Now this is what we have to prove. The extension of the product of I1 and I2 is equal to the product of their individual extensions. So we start the solution like this, by taking these xi, some elements, finitely many elements in I1 and an equal number of elements in I2, these yi's, and we consider the F image of this sum, summation xi yi, where I varies from 1 to n. Because F is a homomorphism, that will be equal to this. F first of all will distribute itself over the sum and then over the individual products. Now because these elements are coming from I1, so their F images will belong to the extension of I1. Why? That is because by definition the extension of I1 contains the F image of the ideal I1, and these are elements from I1, so their F images will in particular belong to I1 extension. Similarly, these y's are coming from I2, so their F images will belong to the extension of I2, and that is why this sum, that is this thing, will belong to the product of I1 extension and I2 extension by the definition of the product of two ideals. But this is just this thing, so F of this sum belongs to I1 extension, I2 extension. But this is how a general element in F of I1, I2 will look. Why? Because this is how, like this sum, a general element in I1, I2 will look. That is why any such F image is inside this product of two extensions. So the F image of I1, I2 is contained in this. Now by the definition of extension, this extension of I1, I2 that you see here on the left hand side is the smallest ideal which contains this as a subset. This product, however, is some ideal which also contains this as a subset. So the smallest nature of this extension makes it a subset of this some other ideal. So that's how we have got one of the two containments that we need in order to conclude equality. Now we will prove the reverse containment. To prove the reverse inclusion, we again take finitely many elements in I1, alpha 1, alpha 2 up to alpha n, and finitely many elements in I2, beta 1, beta 2 up to beta m. This time, however, n need not be equal to n, and we also take these elements in the ring B. B1, B2 up to Bn, you can see that you have this n here and an equal number of elements that we have here. That is B1 prime, B2 prime up to Bm prime, and we need these things because we want to consider this product. B1 f of alpha 1 plus B2 f of alpha 2 up to Bn f of alpha n times B1 prime f of beta 1 plus B2 prime f of beta 2, like that up to Bm prime f of beta m. Now if one does this multiplication, one will get a sum, that is this sum. Actually one has to write a double summation, but instead of writing two summation symbols, I have written only one summation symbol, and there itself I am making it a double sum by simultaneously varying I and j independent of each other, although the variation has not been shown because it's understood that I varies from 1 to n and j varies from 1 to n. Instead we just look at how the individual terms will look. They will be of this form: bi bj prime f of alpha I f of beta j. Now because f is a homomorphism, So this product will be equal to f of alpha I times beta j. And now comes this observation. Such a sum belongs to the extension of I1, I2. Why? Well, where are the alpha i's coming from? The alpha i's are coming from I1 and the beta j's are coming from I2. So what can you say about this product, alpha I beta j? That by the definition of the product of two ideals belongs to I1, I2. Okay. So that means this alpha I beta j, each such alpha I beta j is an element of I1, I2. And what is the extension of I1, I2? That is the smallest ideal containing the F image of I1, I2. But this is one such F image. And this is how elements in this extension look. And that is why this belongs to this extension. Okay. Now let us go back to this product. What can you say about this single sum? This is how a general element of I1 extension looks. Why? Because these were arbitrary elements chosen from I1 and the Bi's are chosen from the ring B. So here you are actually looking at an arbitrary element of I1 extension. Similarly, this is an arbitrary element of I2 extension. And that is why in the next line we write this. So for all x in I1 extension and y in I2 extension, this is x and this is y. X times y belongs to the extension of I1, I2. Right? And that's why I1 extension times I2 extension is a subset of this. And one more thing. How do the elements of this product look? Do they simply look like xy? No. They look like finite sums of such xy's. But if such xy's already are here, then finite sums are also here because this is after all an ideal. So that's how you have this reverse inclusion as well. So combining this one and the previous one, you have equality. And next we have to prove this containment. This time we do not have equality. This one also involves product of ideals and contraction. Contraction because the ideals that we are looking at are ideals in B. So what we have to prove here is this. The contraction of J1, J2 contains the contraction of J1 times the contraction of J2. So we start the solution like this. We take n elements B1, B2 up to Bn in J1 contraction, which by definition is the inverse image of J1 under F, and an equal number of elements B1 prime, B2 prime up to Bn prime in the contraction of J2, which is the inverse image of J2 under F. But then obviously the F images of these elements will belong to J1, that is all these F of Bi's belong to J1, because that's the definition of inverse image. Similarly, the F images of all these Bi primes belong to J2. Okay. Now you look at this thing. F of B1, B1 prime plus B2, B2 prime up to Bn, Bn prime. Using the fact that F is a homomorphism, that equals this. Okay. Now what can you say about this sum? Because these F images belong to J1 and these F images belong to J2, by the definition of the product J1, J2, this sum belongs to J1, J2. But this sum is just this F image. So this individual sum, that is this B1, B1 prime, B2, B2 prime up to Bn, Bn prime, belongs to the inverse image of J1, J2 under F, which however by definition of contraction is the contraction of J1, J2. Now what did we prove? We proved that for arbitrary elements bi's in J1 contraction and bi primes in J2 contraction, the sum formed by their corresponding products belongs to J1 J2 contraction. And this sum that you are looking at here, this bi primes, summation bi prime, that is how a typical element of J1 contraction, J2 contraction looks. That is why any element from this product is here. So that's how this is a subset of this, or in other words, this contraction contains this product.